Again to yet another ZX Calculus seminar. Today we have Boldizsár Poór, who's replacing Wang as the speaker for this week. And we'll be talking about their recent paper together with Razin, Completeness of Qufinite ZXW calculus, a graphical language for finite-dimensional quantum theory. So Boldy, please start.
Thank you. Okay, so so this is joint work with Harney and Razin. Here we establish the completeness of Qufinite ZXW calculus. So what is the Qufinite ZXW calculus? It's the combination of all qudit ZXW calculi. So we have all different dimensions combined in a single framework. And what does this give us? It essentially gives us a graphical language able to reason about anything in finite-dimensional quantum theory. So that's why we think it's quite exciting, and that's what I'm going to talk about today. So first, I am going to explain some very basic preliminaries. First, what the ZXW calculus is. Then just quickly explain what qudits are and what completeness is, and then I will go into the calculus that we establish here and how completeness is proven, and then later on into applications. So first of all, ZX calculus is something we all know, I reckon. So it's an amazing tool for circuit and measurement-based quantum computing or anything also in quantum error correction, because it's a nice model-independent way to reason about these things. But it's not so good when it comes to some other aspects. So, for example, it's not so good to reason about multipartite entanglement or summation of diagrams. So that's where when ZW calculus may come into play, which can exactly do these things, as well as it's quite good to reason about linear optical quantum computing or photonics. And then the ZXW calculus is just simply putting these two calculi together into a single framework. So we have the Z, X, and W generators. And it turns out that combining these two things gives us more capabilities than just ZX or ZW would give us. So we can, for example, express Hamiltonians. Beyond those that are mentioned in this paper, we can also reason about light and matter Hamiltonians in another paper. And we can also express the differentiation and integration of ZX diagrams or ZXW diagrams. This is essentially because the W node enables us to express summations quite easily. So next thing I want to quickly talk about is qudits. So what are qudits? First of all, qubits are the two-dimensional states, right? So we have any state in a qubit expressed in terms of cat0 and cat1. So any state is the combination of cat0 and cat1. And then in qudits, this is not just cat0 and cat1, but also cat2 and cat3 and into cat d-1. So here, any state is in the superposition of d computational basis states. So this is a much larger state space. So some definition I will use in this talk is F-field. So this is the category of finite-dimensional Hilbert spaces. And something else which is important is this F-field D, which is the subcategory of F-field, where Hilbert spaces have dimension d to the power of n. So for example, a qubit would be F-field 2, a qubit would be F-field 3, and F-field D are qudits. And lastly, what's completeness? So if we have two diagrams in a calculus D1 and D2, and we know that they have the same interpretation, so they represent the same linear map, then if we can prove that D1 is equal to D2 using the rules of the calculus, then the calculus is complete. So we have two diagrams and we can prove that they are equal. Then then that calculus is complete. So just a quick recap of history of these completeness results. So first of all, we had Miriam proving back in 2004 that the Clifford fragment of the qubits ZX calculus is complete. And then later, building on the universal ZW completeness result of Omar, it was proven that the Clifford plus D fragment of the ZX calculus is also complete. And later, it was also shown that the universal fragment of the ZX calculus is complete. And then Harney in 2008 proved that qudits, the Clifford fragment of the qudit ZX calculus is also complete. And 2 years ago, Robert and Tituan proved that for all odd prime dimensions, the ZX calculus for the Clifford fragment is also complete. So we have these results. And then last year, me, Arnie, Razin, Leah, Richie, and Bob proved that the ZXW calculus is complete for all dimensions or finite dimensions, but these are only subcategories of finite dimensional Hilbert spaces, right? So we have F2, FL2, FL3, primes, and then all qudits. And then in this work, what we do is prove that that we have a calculus in the whole of F-Hilb, which is complete. So this is going one step beyond what's already there. Okay, so now we have seen why we are excited about this ZXW Qufinite ZXW calculus. Let's see how it actually looks like. So first of all, we will have some qudit generators, and the first one are the computational basis states. So this is just a simple X spider with kj as a parameter, and it corresponds to ket d minus j. Then we have the good old Z spider, which simply corresponds to copying. So if you input ket k, it will output 2 ket k's. And the X spider is just the modulo addition. So if you input I and j, then you will get I plus j modulo d. And then here we will have a notation which we use quite extensively through the paper and also in this presentation. It's the multiplier. It's a very useful little gadget. So what it does is it maps any computational basis state k into m times k modulo d, if the label of the multiplier is m. And because of the hop flow, we can define this multiplier modulo d. So in particular, if we have minus m, that would mean d minus m. So we have had z and x. So the last one is w in the ZXW calculus. So the w, what it does is it maps 0 to 0, 0. And then if you have any computational basis state I, it's going to map it into the superposition of I0 and 0i. So diagrammatically, it looks like this. So if you input ket 0, then you get 2 ket 0s. And if you input any ket j, ket minus j, then you get the superposition of j0 and 0j. So I mentioned the simple Z spider with 2 legs, but we also have phases, as we know. So first of all, we have the Z spider, which corresponds to this diagonal matrix where the last element is e to the power of I alpha. So it's a rotation matrix, but we generalize this to the Z box, where this can be any complex number, not just phases. But we are in qudit dimensions, not just qubits. So in qubits, a matrix would be 2 times 2 dimensional with 1 input, 1 output. In qudits, that's d times d. And thus we have a parameter that has d minus 1 elements. So this is a d minus 1 complex parameters. And these parameters are put into the diagonal of the matrix after the very first one. And generalizing this to arbitrary number of legs, we get the last generator, the Z box. So these were the qudit generators. If someone have read our previous paper, then they might be familiar with these. And the new things are mixed dimensional generators. But first, what are we going to? So something we have to first establish is that now we have mixed dimensions. So we will have to label each wire with its corresponding dimension. So for example, here, this Z spider is a qudit Z spider. So we label it with D. This X spider is a 2-dimensional X spider. So we label it with 2. And then we can also put like 2D or whatever we feel like. And we can't connect wires that have different dimensions. So here, 2 and D-dimensional wires cannot be connected. But if we want to connect something, then we can connect those that have the same dimension. So for example, the 2 outputs of the Z spider could be connected. What else can we do? We can swap these dimensions. So this is just simply one of our generators, the swap. And then the more interesting one is this dimension splitter. So this is the dimension splitter. If you input any ket j, it's going to split it into dimensions of into lower dimensions, m and n, where m times n was the input dimension. And then we can reason in these smaller dimensions. It also has an inverse, or sorry, an inverse. So these two cancel each other out. And it's just going to map 2 smaller dimensions into one bigger one. So then going back to the previous example, if we have a Z spider and an X spider with the very same dimensions, then we can combine these 2 wires into a 2D dimensional wire, and then we are able to connect everything in this diagram. This dimension splitter is associative, so we can label it with any number of legs. So you can have multiple legs coming out of these dimension splitters. The same is true for the dimension merger, so it's inverse. So one of the very interesting things we use is this mixed dimensional Z spider. So it's quite an interesting concept, and to be honest, not so complicated either. So what does it do? So it's going to behave just like the Z spider in the qudit setting up until the minimal dimension. But if you input any basis states that's bigger than the minimal dimension, it's going to give you the 0 scalar. So say that this D1 is the minimal dimension. If you input anything here, that's going to be finite. It's just going to copy throughout all the legs. But if you input here, for example, a basis state that's bigger than D1, then it's going to give you the 0 scalar. And we can define this as the following diagram in the Qufinite ZXW calculus. So we can input ket zeros into the dimension splitters, and then in this larger state space in the middle. So this is going to be the sum, or the product of all dimensions that are inputted. We can express the Z spider, and this will corresponds to the interpretation shown above. So this one. So this is just one more time.
Ollie,
Yeah.
We got a question from Andre Kessin via the text a couple of slides back. It was asking about whether every wire comes with an inherent ordering, all the dimensions, and that's using a dimension splitter, we can, for instance, make a permutation of the base elements that goes like I, J, K, L, and then maps it to, for instance, J, K, L, I. So if I split like a wire into two, and then I do a swap, for instance, and then I combine them again. Does this give you a kind of interesting kind of map, or is this sort of trivialized?
So that's not going to be the identity. So yeah, so if you have this diamond, I'm going to go back to the presentation mode. So if you input, can I draw here? I'm not entirely sure. Anyways, so if you swap here the two wires and do its inverse, the dimension split, then that's not going to be the identity. So it's not symmetric. And it's going to be kind of a weird map. So it's going to do some weird kind of permutation on the basis states of m times n dimension, but I am not able to characterize it off the top of my head now. It's going to be something interesting, and you can also undo it with another round of this, like internal swaps.
So I think it changes the endianness. So here, if you look at the dimension merge map here, if yeah, if you input ij, you get ni plus j. So like j, I is more significant digit than j, so that would like flip the
Yes.
that.
Yeah, exactly. Yeah, that's thank you, Razin. So it's going to make this j, and then this is also, so that would be j times m, and this would be I. Was this the question? Did we answer it correctly?
I think that was the question.
Okay. Anyone else? Anything? I'm really happy to answer any kind of question. Okay. So this was just reiterating on what this mixed dimensional Z spider does. So if you input kj, it's going to copy that kj into the two dimensions. But this is only true if this j is smaller than the two dimensions on the bottom. If j is bigger, then we can't copy it, so you get the zero scalar. So this can be expressed as the following simple rule in our calculus, and this will correspond to exactly zero if j is bigger than or equal to the two dimensions, and it's going to be 1 otherwise. So this is exactly what we just saw, Paul. Another thing we can do with these mixed dimensional spiders is fuse them, which is something we do want to do, but it's going to be a tiny bit different from the usual qudit fusion. So here we have two Z spiders, A and B, labeled with A and B, and then this large M, capital M, will be the minimum of all the wires you see on this diagram. So minimum of everything. And when we fuse these two, then you are going to get a Z spider where the parameter is only defined up to the mth element. So this is purely because of the interpretation. And if you are limited to the qudit case, so all the dimensions are the same, then this is the very same thing as the qudit Z fusion. Another interesting thing is that the trialgebra works even for the mixed dimensional case. So if you have the usual trialgebra pattern, a W and X, and then two Zs, but the Zs have different dimensions on the outputs and inputs, then you can change X to a W. Something else we found, which is a very useful rule, is the decomposition of the dimension splitter. So what we can do is express this dimension splitter in terms of only the Z and X generators. And then we can use this decomposition to prove several properties of this dimension splitter. One last axiom I'm going to mention here is this X dimension chain. So if you have an X spider with dimension n, then you can change the dimension of the X spider to n times m, but you will include these m multipliers on each of its legs, and you will also embed this from an n-dimensional space to an m times n-dimensional space. So this rule comes quite in handy when we prove some of the lemmas using the following lemma. So what this says is if you have two mixed dimensional diagrams and you know that they are equal, so this equals this and they are mixed dimensional diagrams, then that's equivalent to having two diagrams that from where you embed from a larger state space D. So here all the dimensions on top and bottom are D, but you embed these things into this smaller state space and these two equal. So if you can show this, then you will be able to derive this. So these two statements are equivalent. So beyond lemmas and axioms, we also have a normal form in the Qufinite ZXW calculus. It is quite closely related to the qudit normal form, but here obviously we will have mixed dimensional outputs because we need to express any vector of size m, where m is the product of all the output wires, and it is expressed as the following diagram.
Sorry, I'm a bit confused because M seems to be playing multiple roles.
M seems to be, sorry?
At the bottom, you have this M with a subscript, but also this is different from the M.
Yes, so sorry, I should have made this a touch more clear. So this M is the product of all the M subscripts. So M0 times M1 times times MS minus 1 will be M. So if you multiply all the dimensions at the bottom, you get M.
But it's a normal form, so are these the prime factors of M?
No. It's important that you could express something in the prime number decomposition of a number, but it's not necessary. So the outputs, if you are specifying exactly the kind of numbers, then that will specify the type of your diagram, and that's good enough for the normal form.
Right, because a diagram that has two inputs being A and B dimensional is different from having a single input that's A times B dimensional.
Exactly.
Those are different normal forms.
Exactly.
Okay, yeah.
Okay. So the consequence of having a normal form is that our interpretation functor is full. So this is something I'm just remarking here because of something else we will see later on. So just remember, because of this normal form, the interpretation functor is full because we can interpret we can have a diagram that interprets any vector in finite dimensional Hilbert spaces. Okay, so this was something I may have implied, but that didn't make clear so far, is that if you have a mixed dimensional normal form, so here the dimensions are all D, then this is equivalent to the usual qudit normal form. So again, if you have a qubit normal form where the output dimensions are all equivalent, so all D, then this is equal to the qudit normal form. And later on, we will see this comes in quite handy to prove several lemmas. So here I am just going to give a brief overview of how the completeness proof works. And this is the same as the qudit completeness proof. So first of all, we only need to consider states because of map state duality. So having A and B equal as two maps, that's the same as having A and B equal as two states. And then we use this normal form that we have established to prove completeness. So what we do is if we have two diagrams, D1 and D2, then the normal form will be the same of the two diagrams if their interpretation is the same, because the normal form is something unique. So any diagram can be decomposed into several layers of these A1, A2, and so on, where each layer is just the parallel composition of generators. So this is how we will be working. And then what we do is we turn the first layer into its normal form. So what do we have to do? We only have to show that each of the generators can be turned into a normal form. And then we just use the snake equations to bend these wires. And then we turn A2 again into a normal form. So again, what do we need to do? Just turn each generator into its normal form. We then have to show that the tensor product of two normal form is a single normal form. So we have two normal forms, M1 and N2. And then tensoring these two normal forms, you can turn it into a single normal form. And the last thing we need will be to show that the partial trace of a normal form, so connecting two of the output wires with a cup, corresponds to a single normal form. So these will be the things we will need to show. And then if we have this, then we can keep kind of consuming the diagram. And in the end, we end up with a single normal form. So just reiterating what we need to show that all the generators can be turned into a normal form. The tensor product of two normal forms can be turned into a normal form. And lastly, that the partial trace of a partial trace normal form can be turned into a smaller normal form where we don't have the partial trace anymore. So these are the lemmas that we prove in the paper. So these will be first the normal forms that we show is equal to the generator. So first the Z spider is with equal dimensions. So we are not going for the mixed dimensional Z spider here. We are only going for the simple qudit Z spider is equal to its normal form. So if you can remember the lemma where we show that the qudit normal form is equivalent to the mixed dimensional normal form, that's exactly what we use. So because in the previous paper we have established it for the qudit dimension, we didn't need to do much here because of that lemma it follows. The same is true for the W node and the Hadamard box. And where we had to have some challenging equations was the dimension splitter. So here we had to show that the dimension splitter can be decomposed into its normal form, where these Ks and Sk and Tks are specified by these equations. So these were all the generators of our language, the ZXW and the dimension splitter. So that's done. The next thing we needed to show was that the tensor product of two normal form equals a single normal form. And this is the lemma, and you can find its proof in the paper. And lastly, we had the partial trace of a normal form equal to a single smaller normal form. So here Mi and Mj should must be the same dimension, because otherwise you can't connect the two. And then sum k corresponds to the summation of all the indices where S and T matches. This is specified by taking the partial trace of a vector. So having shown all of these lemmas, we have the completeness. So the Qufinite ZXW calculus is complete for finite dimensional Hilbert spaces. So one of the really nice consequences of this is that the category of ZXW, so this is the Qufinite ZXW the category of Qufinite ZXW calculus, is monoidally equivalent to the category of finite dimensional Hilbert spaces FPL. So why is this? This is a very nice little proof. So I am just going to directly show it here. So two categories are monoidally equivalent if there is a monoidal functor between them, and the functor is full, faithful, and essentially surjective on objects. So let's go through all of these points. So first of all, the interpretation functor is a monoidal functor. Then it is full. And so this was something that we have by the normal form. And faithful, this was something we have because of the completeness. And then it is essentially surjective, because for any object, for any element of any vector of finite dimensional Hilbert spaces, we have an object in the category of ZXW calculus such that H is equivalent to C to the power of dmh, which is the interpretation of this object. So this is why the interpretation functor is essentially surjective. So with this, we have shown what we needed to show. So ZXW is monoidally equivalent to the finite dimensional Hilbert spaces. So now we have the Qufinite ZXW calculus. It's a calculus which can reason about anything in finite dimensional Hilbert spaces. So it should be able to express a much richer set of problems than just any qudit dimension would enable us to do so. And we did look into what kind of things our calculus can be used for. And I'm going to show you some of these examples. So first of all, something quite interesting that we have since been working on quite a lot is spin networks. So this is the mixed dimensional Z spider, and we show that the symmetrizer of a spin n over 2 can be represented as the following diagram. So what it will do is it will create all permutations of it will create all permutations, and it will apply this phase to our computational basis states, and that's what we need to have the symmetrizer. And then we did go quite a lot more into this. In fact, we have been working quite hard on this new paper, the Penrose spin calculus, ZX for SU2. And do come to QPL, where we will hopefully give a presentation about this. And stay tuned for the paper when it comes out. So spin networks, very, very promising. Mixed dimensional ZXW calculus seems quite useful for this. Another place where we believe mixed dimensions are useful are mixed dimensional quantum chemistry Hamiltonian. So this is the James Cummings Hamiltonian. Something very similar was shown in the light matter interaction paper, but it did kind of have a problem that the wire that we have here should be something corresponding to matter, where you have only two basis states, 0 or 1. And here, this is light, where you can have any number of basis states up to some limit. So this is something much more closely related to what's actually happening. And we believe that these kind of Hamiltonians can be quite interesting to explore. Another thing we found when writing this paper is that this dimension splitter, mapping smaller basis states into a larger state space, is actually quite useful for quantum programming languages. And one of the things where we found it particularly interesting is that if you embed qubits into this larger 2 to the n dimensional state, apply a Hadamard, and then undo it, that exactly corresponds to doing the quantum Fourier transform. So now we are able to express this whole large diagram as a single quite compact diagram. And it also corresponds quite clearly what it actually does. It applies the quantum Fourier transform matrix on the computational basis states. Just from looking at this, you wouldn't quite get that. But seeing this, it's quite obvious what it does. So we believe this language is very useful for quantum programming languages. One thing that's also interesting to take a look at is mixed dimensional quantum computing. So many times we hear that we have qubit or qtrit or any qudit systems where all the wires or all dimensions will be the same. But we also have mixed dimensional systems where a qubit can interact with a qudit. And these kind of systems actually have quite interesting advantages. You can implement very, very complicated gates with very few number of operations in this mixed dimensional setting. And given that the ZX calculus has been quite useful in reasoning about several protocols in the qubit quantum computing, we believe that this mixed dimensional ZX calculus can be used for reasoning about mixed dimensional quantum circuits and protocols in these. So lastly, what I'm going to mention is since our paper came out, there have been a new paper from Mark and Renaud, Minimality in Finite-dimensional ZW calculi. So they prove a very, very similar result for the ZW calculus. So they have a mixed dimensional W node and the Z spider. And they have quite nice set of rules. So they do consider minimality, unlike us. So they came up with quite a nice calculus, and based on that and our new understanding of these mixed dimensional Z spiders, we have been working hard on developing a new calculus, the mixed dimensional ZX, the finite dimensional ZX calculus. And since that paper came out, we have managed to show that the mixed dimensional ZX calculus is also complete for finite dimensional Hilbert spaces. And thus now we have 3 calculi equivalent to finite dimensional Hilbert spaces, again, on each of them with their own respective benefits and setbacks. But this is it. So if you have any questions, please feel free to ask them either here or later. Feel free to reach out to me on Discord. Thank you for your time, and yeah, thank you.